Okay, so this lecture is basically the kind of wrapping up of Chapter 5 on dense correspondence. And so what I want to talk about today are a bunch of kind of neat applications of dense correspondence related to visual effects that, kind of tie the concepts together. Because I know that kind of moving up to this point, there was a lot of kind of fairly mathematical stuff about how do we calculate optical flow and how do we calculate stereo correspondence and epipolar geometry. So now let's talk about how these things might be used to generate different kinds of effects, okay? And so I want to talk about three main things today, and the first one is called video matching. And so this was a kind of a neat paper several years ago by Sand and Teller. And the idea was the following. So far we've only talked about generating dense correspondence between one image and another image, right? So basically what we have so far is optical flow between, image 1 and image 2. What if we wanted to compute kind of optical flow between two video sequences, right? So imagine that we have basically a whole series of videos, or a whole series of images in one video. This is like, image sequence 1. We could call that kind of a function of t, and then another video sequence. So we could kind of generalize the concepts that we talked about for optical flow, basically saying that, in some sense, for every pixel in one of these images, we want to know where does that pixel go, not only in space, but in time, right? So, I could just do straight out optical flow between every pair of images, right? But, to make this a little bit more general, I could imagine that I could generate the best possible flow by trying to line up images from, different parts of the video sequence, right? So the idea is that, for example, maybe one of the videos is taken at a lower frame rate than the other one, right? And so what I could do is I could say, okay, I want to match the slow video with the fast video. And so I tried to make a kind of a sketch of that in this picture. I don't know how successful I am. But basically the idea being that, A is one video and B is another video. And the idea is that these are two cameras that follow roughly the same trajectory through space. So the curved line is basically the path the camera takes, and then every arrow is one image that the camera takes and kind of roughly the direction it's looking at, right? And so one kind of reverse way I think about this is, well, suppose that I wanted to line up this second image sequence as well as possible with the first image sequence, right? So what I would try and do would be to kind of resample the second image sequence to produce frames that matched up as well as possible with the first image sequence, right? And then once I had those two things matched, I could do cool effects like compositing between these images or cross-dissolving between the images, right? And so, but this is a kind of a tricky problem. But this does come up a lot in real-world visual effects. And so, for example, it's very common to have it used to be very common to have what was called a motion control camera, which meant that the camera moved along this pre-programmed fixed path every time. It was extremely repeatable, right? So for stuff like Star Wars, for example, like the original Star Warses, they would have this extremely precise motion control camera where they could composite in the TIE Fighter, and then they composite in the Star Destroyer, and then they composite in the explosions, right? And so the idea is that if you know that the camera is moving in exactly the same way every time, that means that you can kind of overlay elements, and the only thing you really have to make a decision about is what the relative depth of those elements should be, right? But if you're moving the camera freehand, then it's much more difficult to align these video sequences together, right? And so what Sand and Teller proposed was kind of a software, version of camera motion control based on optical flow. And so the idea was that, I roughly move the camera through the scene, then I change some stuff in the scene, and I roughly move the camera again, and then I try and line up those two video sequences, and then I can do these cool effects, okay? And so basically, kind of what we want to do is we want to, let me go back to my slides here. So the goal is to try to match images from I1 of t and I2 of t as well as possible. And so the details of this, since I want to talk about a whole bunch of algorithms today, I'm not going to get too deeply into this, but let me give you the kind of the big picture, okay? So the idea, basically, is, kind of similar to, it's kind of similar in a way to dynamic programming. What we want to do is we want to estimate dense correspondence between, frame pairs between the two sequences, right? So kind of what that means is, again, if I go back to my picture here, that's like saying, well, what I want to do, let's say I'm choosing this guy. I want to kind of estimate, well, what will the optical flow be between this guy and this guy, this guy and this guy, this guy and this guy, and so on, right? And so what makes, in some sense, a good match is, I kind of want the optical flow vectors to be as small as possible, right? So, I mean, if life is good, there's some image from camera 1 that really exactly matches the image from camera 2. Now, I may not get that lucky, but that would kind of be the best case, right? That would be like saying, hey, here's something where these things really match. That's not exactly what happens in this video matching algorithm. Kind of what happens instead is that, it's hypothesized that a good match minimizes basically what I would say as the sum of parallaxes. And that's a word we haven't used before. What that kind of means is that what I do is I look to see, okay, here's image 1 and image 2, and let's suppose I have a correspondence between them, okay? This could come from an optical flow field. And so the idea was, let's suppose I take 2 points over here, and I look at their distance. And then I look at, 2 points over here that may match, this is basically, if I call this x1 and x2, and this is like x1 hat and x2 hat, well, the parallax over here, you could consider to be like the difference between these point positions. And so what I could do is I could try to basically, minimize this distance, right? That's like saying that, if a pair of points is 5 away from each other over here in image 1, well, then the correspondence should be 5 away from each other over here in image 2, right? The idea is that this is a little bit, this kind of compensates for things like rotation of the image and translation of the image. It doesn't mean that the correspondences have to be in exactly the same place. It just means that if I kind of look at all the possible correspondences over in image 1, that basically they have, fundamentally the same point-to-point relationships over there in image 2, right? That kind of means that the two images are roughly comparable, right, up to rotation and translation. So in a way, you can think about this as a measure of how distorted the image is after you look at the correspondence. Question?
Yeah, so this couldn't detect like scale changes.
Well, this would detect scale changes because if these were 5 away and these were 10 away, then this would have a big error, right?
Yeah.
So this would definitely not be invariant to scale, right? Because there's no.
So it wouldn't be robust to that.
It wouldn't be robust to that, right? So the kind of hypothesis is, and again, kind of the hypothesis that I'm moving the camera around in such a way that, all I'm really hoping for is that the two cameras roughly agree at some point during their trajectory, but there's not like crazy zooming in and stuff like that. So you'll see in the videos I'm going to show that there really isn't any significant change in focal length, so you don't have to worry too much about scale. And so kind of the idea is, again, with a picture, that what I could do is I could say, okay, so let's suppose I fix a frame in the first video, and now I look at the kind of error construed as this kind of difference in parallax between a bunch of candidate frames in the second video. So I kind of have a hypothesis. So my hypothesis may be that here's my first guess about where the match might be, this white dot. And then what I can do is I can say, okay, well, that's what the error at that white dot is. Then I can measure the error a little bit of a distance away from that white dot at these gray dots. So I have like 1 frame away on either side and 5 frames away on either side. And then I get a bunch of errors at those points too. And what I could do is I could say, okay, I'm going to fit kind of a hypothetical parabola to these points and find the place where that parabola is lowest. And that gives me this stripe dot, which is kind of like my hypothesis about the best match that this first frame has to the frame in the second image. And so then I could basically kind of keep on iterating this process. This is the way that I decide for a fixed frame in image 1, which frame should it go to over there in image 2. Okay. Now, there's a little bit of secret sauce in the sense of, you know, don't include changed pixel regions. And let me just show a picture. So I think that this is easiest to illustrate with the original video from Sand and Teller. So let me show you that. Oops, sorry. Which was this one. Okay, so what you're going to see here, and I may stop this occasionally to step in. So what you're going to see here are two videos. One where the ceiling fan is on the desk, and one where the ceiling fan is not on the desk. And these are basically done freehand as the video operator is moving towards the desk, right? And so the idea is that they want to align these two videos as well as possible. If they do that, as they've already done here, this is the post-align video. So here's one. And here's the other one. And here you can see that initially they're not aligned, right? So now they apply their alignment algorithm. And again, what you're going to see here is basically kind of the guts of how they do their optical flow. You can see that these blue lines here are basically optical flow vectors between the original, you know, like just lined up pairs of images. And the orange lines are basically saying these are the places where the flow vectors are really crappy, because usually on things like these moving objects, right? So for example, all the optical flow vectors on the fan are really bad because there is no good match over there to image 2. That fan doesn't exist in image 2, right? So what you see here is that as you look at the optical flow field frame to frame, these optical flow field vectors are all pretty large, right? What you want to do is you want to match the images such that those flow vectors are basically as small as possible. And so here, you kind of see that after the match, so here they basically, you know, done some outlier ejection. This is their estimation of a smooth optical flow field without the fan, and you can see that they've kind of taken care of all those orange vectors. After they've kind of aligned the videos, now you see that life is good. Like the videos basically seem to come together. And now they can do things like look at the difference between the two videos after alignment and start to do matting effects on this fan, right? So what they're going to do is they're going to say, okay, let me change the color channel of the fan, or let me remove the fan entirely. So here you can see the fan is turning yellow, right? Because they're basically taking the difference image and changing the color of the pixels that correspond to the difference image. And then they can start to remove things entirely, right? So they do this again. You know, this is, again, a guy walking down the hall. You know, you look at the correspondences, and then you align the two things. I'm going to skip ahead because some of the stuff that they do has, oh, yeah, this is a good one. Okay. So let's look at this one. I shouldn't have skipped ahead so much. Okay. So this is one that I think pertains to something in this project. So here you've got this, you know, camera panning back and forth as the guy is swinging the glass around on a stick. Then you have the empty scene where you've attempted to roughly do the same thing that you were doing panning with the camera, right? Now you estimate the difference between those two things. And now, once you've done that, you have the background pixels that you can paste in where you saw the wire, right? And so now, if I track the wire, I can just pull in the pixels from the second video sequence and replace them to make this, you know, cool effect, right? So that's the kind of thing that would be difficult to do with like patch-based in-painting, for example. You would never get a video that looked as good as that just trying to steal pixels and put them in. So for those of you that are doing a project that relates to, like there was one, were you doing the one where you're fighting yourself, or is that somebody else? So this might be a good thing where you basically record a clean plate of all the background stuff, and then you try and align things to the clean plate. And let me show you, let's see, skip ahead to this thing here. Oh yeah, so this is a great final example, right? So again, two videos recorded with roughly the same camera motion. Although here the camera motion is a lot slower, so there's a difference in speed, but not in path, right? So there's a substantial effort to align these two things together. And so now you see that the slow video looks a little sped up to compensate, but the effect is pretty clever, right? And then this is kind of like, throw everything in, kind of all the kinds of things you could do with moving a camera around and inserting and removing objects and changing things based on the difference mat and so on. So again, this I'm not sure exactly. The camera motion looks pretty smooth, so I'm wondering. Oh, the camera motion is probably on this train track, actually, now that I look at it. I never thought about that before, but I think that's what's happening, right? So basically, in this way, the train is always moving roughly the same way, so you can align the images to each other. Right? And again, this kind of thing with the orange juice disappearing from the glass, that kind of thing would be very difficult to do with something like in-painting, right? I mean, that you really have to have something that you can steal from some other video sequence. So anyway, so I think this may be relevant for some of you that are working on situations where you want to fight yourself in a video and stuff like that, right? So something to think about. Okay, so any questions about this? Yes?
I guess relatedly from earlier question, so basically, and it seems like that's the case,
Mm-hmm.
example, like the two images or videos
Right.
need to basically have similar paths.
Yes, the two images must follow the same spatial path, more or less. It doesn't have to follow that path along at the same rate, for sure. And that's the key idea, is that you can compensate for little errors in the rate, right? And you can also compensate for, it's not like you have to be like super careful, but you have to be pretty close, right? The assumption being basically that if you were to, that there's some good match along the path where you could say these two things are taken from the same position, and then you could apply an optical flow warp to, make the camera look in the right direction, basically. So again, all this, under the hood, we have to use the fact that, if I have two images that are taken from exactly the same place, right? So if the camera is looking here in one shot and here in the other shot, I can apply a projective transformation to kind of push the pixels over. And if I have an optical flow field, then I can do more than that, right? But you can't do anything when the cameras are fundamentally taken from different perspectives. In that way, you may have occlusions that come from stuff that you saw in one image and you see the other one. Scale changes, stuff like that. So you basically want to make sure that you see roughly the same camera center, to align these two videos up. Okay, so next topic, and one that I'm sure are already kind of familiar with, is morphing, right? So morphing is, an effect of my childhood, basically like the Michael Jackson video and Indiana Jones and stuff like that, where basically you have like one face that you're transforming into another face, okay? And so this process relies on a dense correspondence between the images. And so basically the idea is that I want to kind of, what would be the right word? Smoothly transform one image to another using a dense correspondence. And so let me start by saying, okay, so throughout this example, I'm going to use this picture of this car number 1 and car number 2, okay? So I want to morph these two things one to the other one, okay? And so the most obvious thing that I could do, right, would be basically to say, okay, my morph at a given point, and maybe I also have like a t that indexes the time of the morph. So my morph could be saying, okay, let me take, 1 minus t times image 1 of xy plus t of image 2 xy, right? So when t equals 0, the morph is exactly equal to image 1. When t equals 1, the morph is exactly equal to image 2. And in the middle, it's this halfway combination, right? And so this I would call a cross dissolve, right? So whenever you have a, TV show where one scene fades in the other one, this is exactly what's happening. I'm kind of doing this linear ramp from one to the other. Now, if I were to do that to my car images, it wouldn't look very good. And so I made a little GIF of what that would look like, which I think is this, right? So if I were to do that, right, what I would see would be unconvincing, right? It just basically looks like, it's very clear that one car is faded away and the other car is coming in, right? So I would not want to sell this to the, Hollywood studio, right? So one thing that you could say immediately is, okay, well, the reason this doesn't work is that the cars are different sizes, right? The yellow car is a lot smaller than the white car. And so what I could do is something like, I could try to align two images with basically rotation, a scale, and a translation. So it's kind of like saying, okay, well, what I'm going to do is I'm going to take the car in image 1 and the car over here in image 2, and I'm going to try and find the best mapping from one to the other, kind of like saying, okay, I want to take the bounding boxes of the cars and make sure that they align pretty well, right? If I do that, if I think about doing that, that is basically one answer to the question of correspondence between the two images, right? Once I estimate that transformation, that tells me how to push every pixel from image 1 over to image 2. So what if I did that, and then I tried to do the cross-resolve again? So what would I get? Well, here I would get basically something like this, where, again, not really convincing, right? So here what's happening is that at every intermediate frame of the morph, I'm kind of interpolating between the small car and the big car, deciding what the dimensions should be, and then cross-resolving. Now, it looks a little bit better, but still, all these edges and stuff don't line up, right? Like you can see that the back of the car, there's this diagonal here that turns into a different line here. The wheels don't line up. The windshields don't really line up. The front of the car doesn't line up, right? So there's lots of things that are not so good. And so the answer to this question is, well, why don't we try to make a better correspondence between these two images, right? Now, in some sense, this is not really optical flow in the same way that we talked about it before, because optical flow, the whole assumption is that image 1 and image 2 are fundamentally the same 3D scene, and we're just trying to find how the pixels line up. With these cases of the cars, there is no underlying true correspondence because they're not the same physical object, right? So in this case, you as the user have to step in and try and guide the algorithm to produce a correspondence field that you think looks good, right? And so one example of generating this correspondence field, all right, so let me just say for a second. So let me just show you, so these are some still images of what I showed you. This is the unconvincing morph. So what I could do is I could say, okay, I'm going to make some feature points on this image that line up with the other image, right? So if you guys have started on the homework, hopefully you've already done a little bit of like feature point picking between a pair of images, right? And so in this case, what I did was I had a tablet, like a Wacom tablet, and I clicked on the hood in one image, and I clicked on the corresponding piece of the hood in the other image. And so I tried to find places where the features were easy to match up, right? Since these are both cars, I mean, this wouldn't work if I was trying to match like a cat to an ostrich, right? I mean, you have to have some sort of a sense of what is the natural correspondence between things. But for cars, there's lots of good correspondences. So here's like the difference between this and this. So you can see here, I tried to choose like the frame of the windshield, 4 points along the back of the car that look good, and so on. And so then I can kind of connect those points up into lines, right? And so here what I'm doing is I'm using some of those lines to draw connections between the points. I'm using some of the points to draw connections between them to get basically, basically line-to-line correspondences, okay? And this looks better, right? So you can see this is going to be the foundation. If I could move the wireframe of lines from one image to the other one smoothly, then hopefully the image transition would look good, right? So really what I'm doing is basically this. What I'm trying to do is I'm trying to take each of the images, I'm trying to move them together, move one in the direction of the other so that they're basically directly compatible, and then I'm going to average them, right? So the idea is that if I were to just average I1 and I2 directly, I would get that first example where things didn't line up. If I had correspondence fields so that I could kind of push I1 towards I2 with the optical flow and vice versa, then these two things would match up. And so let me be a little bit more precise about what I'm talking about. So the key idea for a convincing morph is to warp one image to the other. And this warping uses the estimated correspondence between the images. So that means, for example, that let's say I have the two images. And going this way, I have some sort of optical flow field that says, this is how I push pixels over towards image 2. And then going this way, let's suppose I have some sort of backwards optical flow field. Now, in theory, you know, the forward and the backward optical flow fields should be basically negatives of each other if everything matches up, right? But in practice, that may not be exactly true, and we may want to allow for the possibility that these are not exactly inverses of each other. So I'm going to leave this general like this. And the idea would be that what I do is I want to say, okay, now if I want to, say, go a third of the way from image 1 to image 2, what I would say is, okay, I'm going to take image 1, and I'm going to have image 2 over here. And the goal is to make a third of the way morph, right? What I want to do is I want to push all the pixels from I1 over towards I2 using this optical flow field. So this is kind of like saying, okay, what this is basically, it's like saying I take pixels from image 1 and I push them forward by, you know, 1/3, right? In this way, you know, I'm saying, okay, all you pixels go a third of the way over to where you should be to get all the way to image 2, right? And the same way, this guy I'm going to push over with the backwards optical flow. So this is my kind of warped second image. And this guy is going to be like saying, okay, all you pixels from image 2, you guys basically have to go 2/3 of the way over to image 1, right? Because I want to make something that lines up here. And so this is like saying I take, you know, 2/3 of the backward flow and 2/3 of this, right? At this point, in theory, these two guys are spatially comparable, right? I should have flowed everything from image 1 over and everything from image 2 over so that those two images roughly have things in the same place. And at this point, I can say, okay, now I'm going to cross-dissolve these things. And again, if my goal is to have kind of a third of the way over, then this guy here, my final 1/3 of the way image, should be like a third of, or sorry, it should be 2/3 of image 1 hat plus 1/3 of image 2 hat, right? That's like saying, okay, you know, again, since I'm not moving too far away from image 1, it should be mostly stuff, colors from image 1 and some colors from image 2, right? And then as I push the morph all the way through, you know, this thing kind of moves from the upper corner down to the lower corner. More and more colors are coming from image 2, and all the geometry is coming from image 2 as I push the morph forward, right? And so the result of doing that is, first let me see here. So the result of doing that is this. And so you can see that this is hopefully a lot more convincing, because if you look at the rear of the car, for example, right, you never see any sort of artifact for the two backs of the cars not lining up. Same with the front of the car. You can kind of see that since the blue bumper of this car has a little notch in it and the yellow one doesn't, inevitably the yellow one kind of, you know, fills in over the blue one, but spatially everything is good. And the wheels roughly go in the same place. The windshields roughly go in the same place. I mean, you know, you could always quibble about kind of whether this could be better, and it could be better if I added more control lines and tried to really refine. You know, if you look back at my at what I used to do this, right? You know, my lines around the wheels here and so on are pretty crude, right? So I mean, I could have drawn some more lines, for example, along the wheel wells of these cars to try and make them line up a little bit better. And so here are some still images kind of showing that here's the original yellow car, here's the original white car, and then the top row looks like taking the colors of the yellow car and pushing them forward with the geometry of the optical flow field, right? So basically, by the time I push the yellow car geometry over with the whole optical flow field, I should have basically a yellow car that sits in the same position as the white car, right? So that's like saying that this image and this image should be directly comparable, right? And the same way, I can push the white car all the way over with the backwards flow field to make a little white car that basically has the same geometry as the yellow car. Now, basically, at either end, these images look really crappy. And I think I have a zoom in, right? So this is like the yellow car, or this is like the white car with yellow car geometry, right? Looks awful. And this is the yellow car with the white car geometry. But the whole point is that by the time that I generate these images, I'm never using these directly because, like, for example, if you look here, this image here, which is this image here, for example, the quarter of the way morph is saying, okay, take 3/4 of this image and 1/4 of this image, right? So I'm never really using this image because if I were, I would be using a very small fraction of it, right? So it doesn't really matter how bad these guys look at the ends because I'm not using those colors at all to make them morph at those positions, right? So what really matters, for example, is these intermediate images, it's going to be half of this plus half of that to get this, and that's what looks pretty good. So these guys don't really matter, but this is like the halfway, between the two cars, right? And these are the two images that are directly compared. And so you can see that here, this is a pretty credible looking smushed white car, and this is a pretty credible looking smushed yellow car. There's some jankiness around the wheels, but that's all right. We could do better with that. And then when you combine them, you get something that, looks like a car that is like not as yellow as this. So it's kind of like off yellow, but, all the pieces kind of line up in the right way, right? And so, obviously you can do this with faces, you can do this with animals and stuff like that. And so it's very easy to download, morph it yourself kinds of programs where you can draw these lines and points, and then it makes this nice correspondence video for you. So one thing I didn't talk about, though, is exactly how did I go from those lines that I drew on those two cars to generate the entire correspondence, right? That part maybe I didn't talk about, right? So let me say a little bit about that. So when this effect came out, like, people were really excited about it, and the first kind of published paper that, this is the one that you would basically implement in all of your like computer graphics 101 classes. I mean, I don't know if you guys ever do this in your graphics classes, but this is like a very standard computer graphics assignment. And so the idea is that I have some control lines over here. So let's say I have a face, right? And so what I might do, unfortunately I don't have another color marker up here. So what I might do is I might say, okay, I'm going to draw, some lines around the face, and so on. I'm going to draw, a line along the nose and a line along this way, right? So basically, you as the animator or as the illustrator are choosing these lines to basically physically match up on the two, disparate objects, right? With faces, this is pretty easy to do because everyone's face has the same components, basically, right? I mean, it would be tough to do something like, for example, somebody who has glasses and somebody who doesn't have glasses. Then you've got a bunch of stuff on one face that doesn't really match up to the other face. Actually, I guess you're the only odd one out. You're the only one who doesn't have glasses in the room, so no morphing for you. So also stuff like, it would be tough to say, okay, somebody who has like a wild ponytail and someone who has like a crew cut would be tough to decide how should the hair morph, right? So basically what I have is a bunch of line-to-line correspondences. And then to generate the, so now I want to generate basically, I know how basically every point on every line pair corresponds, but how does that help me know, for example, where should this point match up to in the middle of this person's forehead, right? And so the idea is that suppose that I only had one line, okay? So the one line case is something like this. So say I told you, okay, this line over here matches up with this line over here, okay? And now I want to know, how does that single line-to-line correspondence, how can I use that to introduce an entire correspondence between all the pixels from image 1 to image 2? So the idea is, okay, let's suppose that I pick a point over here, okay, and I want to know where is the correspondence to that point. What I do is I kind of measure, okay, so with respect to this line, how far away is it as a normalized distance? So I might say, okay, for example, you know, this distance here is a number between 0 and 1 that tells me how far along the line is this point. And then there's another distance here that tells me how far away is that point from the line, right? So instead of representing that point as x comma y, I think about it as alpha comma beta, where, and if you think about it, you know, even for points that are outside here, you know, here alpha would be negative, right? Because I'd be moving across, you know, so here alpha would be like less than 0, and here alpha would be greater than 1. That's okay, right? Now, what I do to generate the correspondence is I say, okay, I move the same relative distance over here, and then I move the same absolute distance out to here, and that generates a correspondence, right? Now, you could argue all day about whether this is the right correspondence or not, but this is one way to do it, right? So in some sense, this single line generates for me correspondences between all of image 1 and all of image 2, right? Now, what happens here, though, is I have lots of lines, right? And so, in some sense, the idea is that this makes, you know, a reasonable amount of sense when I'm close to the line, right? So certainly it makes sense for points that are right on the line, and points that are not too far away from the line, it also kind of makes sense for. The idea is that when I have multiple lines, you know, so say I have, for example, 2 pairs of lines. So let's say here's line 1, and here's line 2, and here are the corresponding lines over here. Well, let's consider this point again, right? So that's like saying, okay, according to line 1, I would move out this way and move over this way. And that would put me a correspondence over here. And according to line 2, I would move up this way, and I would move over this way, and that would be like maybe over here, right? So basically the problem is that this point may map to 2 different places over here in the second image, right? Every line kind of gives me an opinion about where that correspondence should be. And now the idea is that what I do is I actually weight the, you know, proposed destinations by proximity to the original lines. And so what I mean by that is that if this point was really halfway between these 2 lines in the first place, then I would just kind of say, okay, I'm going to split the difference and say this is my hypothetical correspondence, right? If this point was like a lot closer to this line in the first place, well then really what I do is I say, okay, well I don't really care, you know, maybe this is the hypothesis from line 1, this is the hypothesis from line 2, but I say, look, you were so close to line 1 in the first place that really I'm going to choose something that's very close to that original point. So it's kind of like a weighted distance between how close I was to an original line. And so in this way, lines kind of have like a local area of influence where all that stuff to them, close to them, gets pushed right along with the line correspondence, and stuff that is far from any line is kind of pushed and pulled by different line segments according to how far away they are, right? And so, you know, again, this is just a heuristic for obtaining correspondence. You can't really defend this on any sort of true correspondence field grounds. This is just a quick way for an animator to draw lines on the image and then obtain correspondences that move along. And so again, if you don't like the correspondence that you get, then you can always add more lines, and the more lines you have, then the closer a given point of the image is to any one of the control lines that you have. So basically, this is just a picture, I guess, showing exactly that, right? So here, you know, this is the single line case where I use one line segment to produce this corresponds xi prime. Here's the other case where if I have two lines, my correspondence would be somewhere, connected, somewhere between this guy and this guy, depending on how close I was to the original line. And so this is just an illustration showing that, this is just an illustration showing that what happens to the lines from image 1 and image 2 as I push them over. This is the correspondence I showed you before. This is actually the morph I showed you before. So again, this is the kind of thing that you can easily, if you just Google, image morphing app, you'll be able to find an application that lets you draw these lines and then generate the morph. I will say that I wrote it in MATLAB myself, and it wasn't that hard to do. So it's not something I considered assigning it to you as homework, but I decided to give you the other one instead. But that is something that's very straightforward to figure out how to do. Okay, one other comment about this is that actually, even though if I go back to my if I go back to my cross dissolve here, right? So this is basically saying that every pixel xy kind of moves from image 1 to image 2 at the same rate, right? That's not necessarily required. I mean, what I could do is, I could do, per pixel temporal effects. What I mean by that is that, again, suppose I have two faces, for example. So what I could say is, okay, maybe I'm going to morph the eyes of this person. Like maybe I'm going to say, okay, everything above this half of the face, maybe I'm going to morph this faster, and I'm going to morph this part slower, right? I mean, there's no reason that you have to have every pixel obeying exactly the same rate of morph, right? And so you could have a whole other layer of complication by saying, okay, now I'm going to develop a temporal field that tells me what is the function of t that gets me from image 1 to image 2 for this pixel, right? And then you can do all sorts of kind of funky effects, right? You can go back and forth. There's no reason why everything has to move all at once. Okay. So any questions or comments about this? All right. Like I said, I think you've probably seen this effect before, certainly, and now you kind of know how it works. Okay. Okay. Next topic, though, is just a note. Even if the correspondence is perfect, morphing can't or doesn't produce physically consistent images. So what do I mean by that? Well, what I mean is that even though all those intermediate images of the car looked pretty good, one of the reasons was that the car was fundamentally, facing the same direction in both of the images, right? It wasn't like I was looking at the front-on car in one image and the side-on car in the other image and trying to morph between them, right? Here's an example that shows that, so here what I have is basically two images of this little sheet of stickers, right? One that is taken from the front and one that is taken from the side, okay? Now, since this is a plane, all of the pixels in this pair of images are related to each other by a projective transformation. That means I know exactly where the correspondence should be between every point on the sticker sheet in image 1 and in image 2. Now, if I just apply this morphing algorithm I just told you about, I get this resulting morph here that looks really weird, right? The sheet of stickers seems to be bendy and curvy, right? And the reason for that is that there is nothing in my cross-dissolve equation that tells me that the morph corresponds to what you'd get if I moved the camera and looked at the image again, right? So morphing is an entirely 2D process, right? It's just pushing image pixels around. Whereas to really understand how to make a new view of something, I have to think about how would these pixels look if I physically moved the camera and took another picture of it, right? And so we need a little bit extra stuff to say, okay, well, if the camera substantially changes perspective between the two things that I want to morph, then I can't just do the morphing algorithm. I have to add something else to make sure that those images look like they would have been generated by a moving camera, right? And so even though I didn't do the experiment here, you would have seen something similar had I taken like, the front-on car and the side-on car and tried to make matches between them. The morph between them would have looked really weird. Like the car edges would have seemed to bend, straight lines would become curved as they went from one place to the other, right? And so this gets a little bit into what we're going to talk about on Thursday, which kind of relates to camera geometry and how cameras are used to produce physical images from the scene. But we can talk a little bit about that now without knowing too much about it. And so this is an idea called view interpolation and view morphing. And so sometimes you also see this called virtual view synthesis. And to be honest, this is some work that I was involved with like 12 plus years ago for my PhD thesis. I was doing virtual view synthesis. And so I'll tell you the story in just a second. So basically, this is building off of a couple of key papers, view interpolation by Chen and Williams, and view morphing by Seitz and Dyer. And so the idea behind this first algorithm, view interpolation, was the following observation. The idea would be that basically morphing does produce physically correct images when the cameras are in a particular configuration. What do I mean by that? Well, this is the configuration that we're talking about, right? So for this to work, here these white boxes are the original kind of camera viewpoints, and the striped box is the thing that I'm generating with my kind of interpolation and morphing, right? So for this to work, basically, we talked about this camera baseline, right? The baseline is the line that connects the two camera centers in 3D space. So here, what Chen and Williams showed was that if basically I am looking straight ahead with respect to the baseline, so I take a picture like this, and then I move along the baseline and take a picture like this. So both of the image planes have to be parallel to the baseline and parallel to each other. So it's kind of like literally I'm translating a camera looking straight ahead along the baseline, right? So that's a fairly restrictive kind of camera motion. But it turns out that in those cases, I can generate intermediate scenes by matching up pixels and looking at their averages that actually you can show, and we can show this in the next chapter in one of the homework problems if you want. You can show that actually the average of these corresponding image pixels corresponds to where would that 3D point project to in this striped image. And so here's an example where this image and this image are basically two original images that satisfy this assumption. And these two images are synthesized by averaging corresponding pixel locations. And you can see that these images look like moving the camera around the box, right? So these images you look at and say, okay, yeah, these look reasonable, right? These look like they could have been produced by a camera moving from here to here. And I have a little GIF of that I can show you, right? So this is like, two of these images are real and two of these images are synthesized, right? You can kind of tell the synthesized ones by the weird green artifacts in the background. And also, the real ones look a little bit sharper than the interpolated ones. But still, this gives you the effect of kind of moving the camera back and forth in front of an object, right? So this is okay, right? But what happens when your cameras are not in that configuration, right? Well, the interesting observation that Seitz and Dyer made was, I'll come back to it, was that, even if your cameras looked a little bit weird, right? So for example, say these were the original perspectives of your two cameras, right? So you've got some baseline and the cameras are just like arbitrarily oriented, right? What I could do is I could apply a projective transformation called a prewarp to just rotate these images so that they do satisfy the hypothesis of view interpolation, right? So basically I take these white images and I just apply a projective transformation to produce these gray images that satisfy my requirements. And then I use view interpolation to make this other gray image, right? This one is also going to be physically consistent. And then I apply some other projective transformation to effectively rotate the camera. So I can basically make any new interpolated image I want just by doing this initial step of, actually this initial step is exactly what we talked about when we said rectifying the cameras, right? So remember we talked about in stereo and f-polar geometry, we talked about this process of image rectification. And that's exactly what this pre-warping technology is rectifying the images so that the f-polar lines are horizontal, right? That's exactly the process, right? So now you kind of know why I talked about rectification. In addition to stereo, this is the first step that we need for view morphing, right? And so here's an illustration of that, right? So here are the original two images, okay? These guys are not rectified, right? And I can tell that, for example, by saying, okay, well, if I look at this edge of the box, clearly the endpoints of this edge don't fall on the same scan lines as the endpoints of this edge, right? So the first thing I have to do is I have to rectify the images by estimating these projective transformations that will bring the epipolar lines into this horizontal position. So these guys at the bottom left and right are what you get after you rectify the images. And now you can see that, if I look again at this edge of the box, that yes, now this looks like, if I were to follow my mouse over, that all of these top corners would lie on the same line, right? Now I apply a view interpolation algorithm simply by basically, taking an average between pixel positions and corresponding scan lines, and I produce this image here that is basically a reasonable looking image of the box. And now I can apply any projective transformation I want, which kind of corresponds to rotating the camera around to make a new final image, right? And so again, what I can do if I were to finally sample this would be I could rotate the camera kind of from this position to this position, and that's what I do in this case here, right? So now this is kind of a crappy looking image because I kind of just whipped it off last night. But basically the idea being that here what I'm doing is I am interpolating between the two endpoint images with this view morphing algorithm, and now this is a much richer effect than I can achieve by just simply, doing view interpolation. Now it really seems like the camera is moving around the object in a physically convincing way. Now if the box had different colors, right, so if the box, for example, was actually a different box in image 1 and image 2, then what I would get would be this kind of simultaneous camera viewpoint change as well as intensity change. And actually I don't have a great example of that here, although maybe if I were to just Google it, I would see the famous view morphing example.
What they did for matrix?
Yeah, we'll talk about that in just a second. So yes, this is related to the matrix. So here's the idea of, here's this guy on the left, and here's this guy on the right. So the camera position is different, and the people are different, right? And so when you view morph between them, you get basically this intermediate guy who is like halfway between the two people and halfway between the two camera perspectives. And so, let's see if this will work, right? So, again, to make this morph, you have to do everything that you had to do for the original morphing algorithm in terms of making correspondence between the things, and then you have to do this additional step of making sure that you rectify the images, do the morph, and then change the camera back. So this has a bunch of fun examples of, for example, going back and forth between, the Mona Lisa, the left image and the right image. Again, you have perfect correspondence between those two things because you're just flipping the image, and then you can kind of change the camera viewpoint as if the Mona Lisa was looking forward instead of to the side, right? So this is a really fun kind of algorithm. Again, this is really the best example of the case where you're exploiting both the camera change and also the intensity change, right? So yeah, it's a cool effect. And this picture here is kind of meant to say that there are a bunch of little things that you have to take care of when you're doing this effect. Basically saying, okay, for example, what happens when you've got a point like image C where it's not actually seen by any of the two original images, but there should be something from the synthesized point of view that fits in there, right? So there's kind of this hole filling or in-painting problem where you have to fill in stuff that you didn't see from either camera. Or something like, I think that I was getting at here is that, here, both of these cameras can see points A and B, but those 2 points kind of fold over when they're seen from the perspective of this middle camera, right? So I have to make some decisions about what is the right depth ordering of camera, of points if I have, 2 competing possibilities for what appears at this pixel in the synthesized image. Question?
Yeah, how would you actually, if there's no information in C in either of them, how would you?
Right. So basically, I can show you an example of that in something that I did. So let me show you my PhD thesis research, because I don't get to pull it out very often. So I was basically funded throughout my PhD career by IBM in Japan, who wanted to develop technologies for the World Cup when it came to Japan and Korea. I think in 2002, was that when it was? It was a long time ago, right? And so I was a grad student like from 96 to 2001. And so basically, IBM really wanted to develop some cool-looking technologies for when the matches were broadcast in Japan. And so the first thing I did, which I didn't show here, is basically to take the images from a rotating camera and make a big mosaic out of them, and then put the players back on the field like a kind of a time lapse, right? Which again, I think that there's one project in here, someone wants to do the same kind of thing with soccer video. I guess this is soccer videos, so they could duplicate my PhD thesis, right? So the other thing I did was kind of applying this view morphing idea to video, right? And so you could make this even more complicated by saying, okay, well, actually, do I have a picture of this? No. So you could kind of say, okay, I could do virtual video synthesis, right? So the idea is that if I have a bunch of images from one video stream and a bunch of images from another video stream, I could basically do all sorts of I could do all sorts of crazy effects to generate, intermediate images that seem to, for example, swing back and forth between the 2 video sequences. And so let me just show, for example, what if I were to apply view morphing to just a pair of still images, right? So let me just go back to this for a second. So here I have 2 images. This is kind of typical of what you get when you see broadcast sports, right? You've got like one wide-angle field of view and one kind of more close-up field of view. But again, with with sports video, you can be pretty sure that these cameras are all synchronized, right? Because when you switch back and forth between cameras, you don't want to have any sort of temporal lag between the cameras. So all the sports guys have figured this out already. And so first thing I have to do is synthesize the correspondence between these 2 images. And so in this case, what I did was I used a kind of a crude assumption that there was a projective transformation that related the plane of the soccer field, right? Because the soccer field is a plane, right? And so 2 images of the same plane are related together by a projective transformation. So that takes care of pretty much everything green here. And then I had to do some manual segmentation of the objects, right? So I had to segment the players and the ball, and I did this manually, I'm sorry to say. And then if you just apply basically straight out morphing between the 2 images, you get this is view morphing, you get this kind of nice continuous effect of, it looks like you're physically moving the camera while everything is stationary, right? And so you're talking about the matrix. So this is kind of like the matrix bullet time effect, except without any, the matrix bullet time effect was done with like a zillion cameras, and you're actually interpolating between the cameras. And they did do something similar for the Super Bowl. When the Super Bowl was broadcast in, I want to say like 2001 or something like that, Carnegie Mellon University developed this thing called iVision, where basically they mounted these very, very high-quality cameras around the periphery of the stadium, and then they were able to deliver these effects where fundamentally, for an instant replay, for example, they could say, okay, why did that guy pass the ball the way he did? There was a guy with a knob in the control room where basically you're kind of turning the knob to see the action from that guy's perspective, and you can see there's like this big open lane. That's why he passed the ball down there, right? So there's this kind of cool matrix-like, thing that they did. But again, all that was done with many real cameras that you were basically switching between, right? Whereas what I was trying to do was what you could push from a single pair of cameras, right? And so this is what you can get if you just did view morphing between these 2 things. And you can see that, again, things look pretty good. Clearly, there's some stuff that doesn't look good. So for example, these guys here who appear only in one image, I don't have any information about how they should look in 3D, right? So they kind of follow along as if they're on the plane of the soccer field, right? Similarly, all this stuff in the background, right, that really doesn't lie on the plane looks kind of weird and distorted. But everything that's actually in the middle, like kind of the cross between these two things, does look pretty physically reasonable, right? And the players and the ball look like they're kind of frozen in time, right? And so again, what I was doing, and I don't want to belabor the point, but what I was doing was I was trying to estimate so I estimated the epipolar geometry between these pairs of images. Then I estimated correspondence along those epipolar lines. And the correspondence was complicated because, for example, look at this red guy and this blue guy. They switch places, right? So in some perspectives, the blue guy is to the left, and some perspectives, the blue guy is to the right. And so what this means is that I had to deal with this double male illusion that we talked about, right? This non-monotonicity means that the correspondence is not like this nice matching path from one corner of the graph to the other. I have to actually have pieces of the graph that correspond to stuff that's non-monotonic. I don't know if I have a picture of that on my, I don't know if there's a picture of that on this webpage. Well, let's see, for the sake of argument. Right. Man, these are the days. So, this is a short paper. Okay, so nonetheless, like here you can kind of see that if I make this a little bit bigger, whoops, not this. What's the, I guess Alt plus maybe? Control plus? So what you're seeing here basically is this is the scan line in image 1. This is the scan line in image 2. This red blob here is a player on the field, right? And the problem is that the player, so here what you're seeing is that, the blue here is basically the correspondence between the two scan lines. And you can see that this is not a monotonic correspondence from one corner to the other because this blue guy is, kind of not satisfying those requirements. So there's basically some grass that's occluded over here and some grass that's occluded over here. You were asking the question, someone was asking the question about what happens when you have a hole that's left by, so you can't see any other image. So I think in my case, since I was dealing with soccer video, I had a bunch of holes that I just filled in with green because the green is the color of the soccer field, right? So there were a lot of cases where there was a guy and then he had two shadows that I hadn't seen from either I hadn't seen from both images. So when you only see it from one image, you can steal the color from the other image. When you don't see it from either image, you have like a default color that you fill in, right? So there were a lot of heuristics to make this video. Okay. So then let's talk about, so what did I actually do? So then the idea was, okay, well now what I could try to do would be to, and maybe I have a picture of it here, actually. Yes, so this is kind of a picture that goes along with what I was trying to do. So the idea was that here, what's happening is that you have, one image sequence and another image sequence. At every time frame, I basically rectify the images, and then I try and make a morphed algorithm out of these rectified images. And then, the cameras are only rotating between successive instants, right? Because it's like usually there's a person who's operating the camera on a big dolly or a swivel, right? So all they're doing is they're changing the camera rotation. And so in theory, the rotation matrix describes what's happening between two successive images of video. And so what I tried to do, which was not like 100% successful, was to estimate the epipolar geometry in the first pair of images, estimate the projector transformations that related the next sequences of frames in the video, and then I tried to push the epipolar geometry forward into the next frame, and then kind of do a little bit of an update of that epipolar geometry to make it conform to what you actually saw in the image. So let's see what that turned into. So that turned into this video. So what you're going to see here, what you should see here. So the video starts with the same kind of moving the camera with everything still, but then once you've got these two video sequences, you can actually start to slow down or speed up or reverse the action. And so here's, kind of like my attempt to be a little bit more matrixy. I guess I can make this a little bigger. And so what you're seeing here is the first part is like regular view morphing, and then the rest of this stuff is what happens when you kind of try to push the view morphing forward in the video. And you can see that, some things look okay and some things look kind of crappy. I mean, I can say this now. So, like, you look at this guy's head, for example, it kind of separates from his body and moves up off the field, right? Part of that, so what's happening there is that basically I didn't do good enough of a job of accurately maintaining the epipolar geometry between the image sequences as the time went forward. And so that meant that I didn't have good matches for this guy's head in one image and the other image, right? So you see a lot of heads floating around. That's not so good. The other thing that's kind of funny is that you can see that these guys here, this trio of players, like initially they're off over here, and then they kind of walk over this line, and they start to pop over the line, and they suddenly become three-dimensional because now I've seen them in both image sequences, and I can estimate their correspondence. And so initially they look like they're just walking along the flat plane of the field, and then they pop up and start walking along. But things don't look horrible. I mean, I can see that by today's standards it looks pretty bad, but at the time it was pretty exciting. And I think that, knowing what I know now about computer vision, I could do a lot better with this, right? So really what I would want to do would be to really try and accurately estimate the stereo correspondence at every frame of the sequence. If I have a good stereo correspondence, then I can make a good virtual video, right? My problem was that I didn't have very good correspondence as the video went forward in time, right? But anyway, at least now you know partially what I got my PhD for. Okay, so I think that's actually, let's see if there's anything else I want to say. Yeah, so like I said, this is definitely related to bullet time, kind of stuff. So bullet time, actually, we can probably just see for a second here. If you haven't seen it before, I'm sure there's a, yeah.
So in the use synthesis, and you had the pre-warp and then
Yeah.
and you interpolated that post-warp. That post-warp step, like, is that like just inverse of the pre-warp?
Right, so let me just talk about that for a second. So basically, this is the view morphing idea, right? So I have to rectify the images in order to do the initial correspondence. The post-warp is really up to me, right? I can apply any projected transformation I want to produce the final image, right? It's arbitrary, right? So one thing that you can kind of do is say, okay, suppose I choose like 4 points here and 4 points here, and I want to say that those 4 points should basically kind of follow along, right? So for example, one thing that you can do is say, okay, I want to fix the motion of this one planar object as it moves from one image to the other. Then you can use that 4-point motion to pin down what this transformation should be, right? But yeah, you have total freedom in choosing the post-warp. You can move that camera however you want. Ideally, you should move it in such a way that it kind of makes sense to go from here to here, right? Yeah, but so there is a choice at that point. That's a good question. Yeah. I'm surprised actually that my bullet time matrix is not. Let's try camera array. Boy, I'm kind of surprised that this is not like the first. I know what I want. Yeah, so here's an example, right? So basically, this was an example of the camera array that they used for like the rooftop fight in the Matrix. So it's a whole bunch of cameras that are on this kind of, I guess it's not actually on a rail, it's on a zillion tripods, right? And so these are all synchronized. And so fundamentally what you saw during the rooftop fight was a judicious choice of deciding which cameras were used to form the Neo shot, right? So basically, the places where he looks like he's suspended in midair is because basically time is frozen and you're rotating which camera you're asking about, right? And then you can kind of slow down or speed up things depending on how quickly you move time as you move through the camera array. So if you have a zillion cameras, you can duplicate this array yourself, right?
Do they actually interpolate between like nearby cameras?
So that's a good question. Did they interpolate between nearby cameras? Oh, this is the famous picture, right? So I don't think that, so they must have done a little bit maybe to clean it up, but I mean, I don't think that since the cameras are so close together, I don't know that they had to do a ton of that. And again, at the point where you've got two cameras that are so spaced, so close together, then you could just use some sort of optical flow probably to get the alignment just right. Yeah. Yes. So again, this again came out when I was in grad school. It was like, oh my God, how did they do this? And then that's kind of what inspired me to do some of the stuff I was doing. So, Okay, other questions about anything? All right, so like I said, there's lots of interesting stuff to read about in the interview section at the end of this chapter about how people use optical flow and morphing and stereo in feature films. And like I said, this is really kind of a key technology for lots of visual effects. And so what we're going to talk about next time, basically, is how do we move our discussion and analysis into 3D. So far, I haven't really talked too much about the